This video is an example of using the first law of motion, or at least recognizing the first law of motion in a pretty standard example of dropping a ball. So the ball just falls down towards the ground. Yeah, so I'm going to drop a ball, and I'm going to put in that the ball has a weight of 10 newtons. Very carefully, this thing right here, this value is a weight value. It is not a mass. Mass is values in kilograms, and it's true that this ball, regardless of what it's made out of, is going to have some sort of mass. But that's not what I've described here. What I've described here is how heavy the ball is. Actually, what I'm describing with this 10 newtons is the fact that the Earth is pulling down on the ball with a force of 10 newtons. That is, the Earth's force on the ball has a strength of 10 newtons, and the direction is down towards the ground, or down towards the center of the Earth. So let's think about this, and then I'm going to show you how to recognize or see Newton's first law of motion. And it's kind of strange because it's really simple, but it's also pretty tough to see it. Yeah, so let's see what happens. So here's the ball, picture of it right there, and I'm going to describe to you its motion, but I'm going to describe how its motion is changing as well. So I'm going to say that it has a velocity of 0, it's at rest, but not only that, it's in a situation such that its motion is not changing, it remains at rest. That is, the velocity is a constant value of 0 for some small amount of time. And it's the time during which a hand, so here are some fingers of the hand. That's a terrible hand. So here's somebody's hand holding up a ball. Their fingernails. So this person is holding up the ball. So they're supplying a force, this person is. But I just told you that there's actually a couple of forces on this ball. There's also a force by the Earth pulling down on the ball. So this 10 newtons of force by the Earth is, we call it the weight force. So that there is a weight force acting downwards on the ball, 10 newtons. But there is also, I guess, the hand is supplying another force, pushing up on the ball, right? So you have to support the weight of the ball or hold the ball up. This is the holding the ball up, or supporting the weight of the ball. Sometimes people call this a normal force. Or a support force. So you've got these two competing forces. They're in opposite directions with the same magnitudes, and they both are forces upon the ball. This is the force by the hand on the ball, upwards, and this is the force by the Earth on the ball, downwards. Two completely different forces. They just happen to have the same size and point in the opposite directions of each other. In this case, because the motion is at rest, we can also say, because F net is equal to 0, so F net on the ball is 10 newtons upwards, that's the support force, plus 10 newtons downwards, that's the weight force, and that adds up to 0. And by Newton's first law, whenever the net force is equal to 0, the object is not going to accelerate. And when the object doesn't accelerate, it just remains with whatever motion it had. In this case, the motion that it had was no motion. So because the net force is 0, it's going to remain in that situation of motion. It remains at rest. So, but we're talking about dropping a ball. So let's drop the ball. What that means is you're going to remove your hand. And once you remove your hand, you can no longer cause the 10 newtons of support force. That is, where we're going to remove the support force. So all of a sudden, here is the ball. The earth is still going to pull down on the ball. That's the earth's weight force on the ball. But there is, right, we just pulled our hand. The hand is somewhere over here. So all of a sudden, we have what's referred to as unbalanced force. Over here, the forces, there were multiple forces, and they were able to balance or cancel each other out. Over here, we don't have a balance of forces. It doesn't balance up to 0. F net actually is equal to 10 newtons. There's only one force, it's downwards. So the net force on the ball is 10 newtons down, and that is definitely not 0. So according to Newton's first law, it says that whenever the net force is not 0, the object is going to accelerate, or the object's motion will be changing. And that's in fact what you see. So after you drop the ball, what happens is the ball picks up speed. But what's interesting to do is, let's say this is right after you drop the ball. It picks up a little bit of speed and is moving down with some speed. But if you check a little bit later in time, it will be moving faster downwards, and this force is still acting on it. That weight force is still acting. And that weight force, what it's accomplishing is causing the motion of the ball to increase in the direction of the net force. And that's in fact what you notice if you go out and you do this experiment. What the experiment will tell you is, it's interesting, that the motion will, every time you check it, all these moments in time, whenever the net force is not 0, the ball will be picking up speed in the direction of the net force, ultimately. Yeah, so this is, I hope it's straightforward. It's a use of the first law of motion to analyze dropping a ball. Interestingly, if you can probably imagine this, but what if the ground is down here? When the ball shows up at the ground is going to be able to begin to supply a force depending on sort of how much of the ball is touching the ground. Yeah, it's sort of tough to model this particular force. This is the force on the ball by the ground, by the structure of the dirt, or the bricks, or the clay, or whatever the ball is impacting with. And also, honestly, the structure of the ball itself. Is it a steel ball or a rubber ball? And the truth is models can become quite complicated. But nonetheless, you know that the ball is going to impact the ground headed very, very fast downwards, right? It'll have some really fast speed when it gets here. This 10 newtons weight force is never going to change. It's always going to be this certain amount of weight. So that 10 newtons of force downwards is going to be constant all the while the ball is hitting the ground. But depending, like, it could be that the force by the ground on the ball could be very, very large. Let me draw this to the side. So here is the ground. Here is the 10 Newton force. And maybe at some point during the impact of the ball with the ground, we could see 50 newtons or 500 newtons, depending on if this is a steel ball or a rubber ball or a foam ball. So let me just put in something extraordinary. So how about 100 newtons? And then the balance of forces, F net, on the ball is 90 newtons upwards. And the ball will experience an acceleration that's upwards opposite to the direction of the motion, and that's why the ball is going to stop. That upwards acceleration on a downward moving object, that upwards acceleration removes motion, and that's why the ball can stop.